Hi everyone. So today I'm gonna start to talk with you about chapter 1 in Math 130. Um, Before doing that, I would like to make sure uh, answer some question like why we have to learn calculus. Okay. Um, so as you see in these pictures, we're gonna learn calculus in order to determine where a plot, where a pilot should start to descend for a smooth landing, right? Okay, so I'm gonna say, let me write. Okay, over here, where a plot, a pilot, sorry, always a pilot should start to start the descent for a smooth landing. Smooth landing. Okay. And also we're gonna determine the length of curve to design, right? Length of curve to design. Okay. So this is like a gateway arc in San Luis. Okay. What is this? So we're gonna measure amount of light have seen by human eyes. Okay, um, so let's say measure amount of light, right? And then we're gonna compute force. Okay, something like that. So this is the reason why we have to learn calculus. So let's start with section 1.4 here, which is talking about exponential function. So what is exponential function, and which is a power function? How can you recognize, right? So you should know that for f of x equal to b to power x, that's gonna be the form of exponential function. So in here, you should know that the variable is on the top, right? And b is base. Okay. So now you can see that fx equal to power x should be exponential function. Okay. And the other ones is power function. Okay. All right. So this is the graph um, of these two functions. The red line is for 2x. The blue line is for x squared, right? So which one is grow faster? Which grows faster? Okay. say, let's choose x equal to 8. We're gonna have y for the exponential one. I have y equal to 2 to the power 8. We equal to what? 256, right? Well, y equal to x squared. I'm gonna have 8 squared, which equal to 64. So clearly, the exponential one is faster. So exponential. So exponential is faster. Okay. All right. So now let's take a look at the definition of exponential function down here. You should remember that the base had to be greater than 0. Okay. And the exponential function should be in the form as p, let's say p0 multiplied by b to power t. Okay, and in here p0 is a constant. So p0 equal to f of 0. That means what? Like whenever t equals 0, then the initial value is f of 0 gonna be equal to p0. Okay, so also b in here is gonna be the factor by which f change when t increase by 1. Okay, so what does that mean? Let's say f of t plus 1. I want to find what is that going to be. So let's substitute it. I have p naught term with b to power t plus 1. Now I have to change the t to be t plus 1. Okay, because now input is t plus 1. So this t, let me use other colors. This little t now change to be t plus 1, because now input is t plus 1. Does that make sense? So that's gonna be equal to what? P0 time b to power t, and I can write another b here. You know what? I can just slow down and have one more step like this so you can understand, right? You know that bt plus 1 can be rewritten as bt times b, right? So now I can have p0 times bt, sorry. I'm gonna have a parenthesis here. It should be still the same, but I just wanna have a parenthesis here so you can know that what is this. It actually is ft, right? It was ft, and now it's multiplied by b, right? So what does that mean? In conclusion, you know that f of t plus 1 will be equal to f of t times b. All right. So that's the reason why I say like the B is a factor by with F change when T increases by 1. Okay. Okay, so um, let's the left hand side here we're gonna graph if in the case that B greater than 1, and you should see the graph of the exponential function look like increasing increasing um, from 0 and going up. Okay, and the intersection or the y-intercept over here, it should be the point at 0 comma p 0. Okay, and this should be function as y equal to p0 times b to power t. All right, and since the curve exponent here is will never touch t equals 0 over here, then it's called asymptote here. Asymptote. Okay. And in this case, it's called exponential growth. Okay. Because it's growing out, right? And domain in here gonna be all real number. In the interval, say from negative infinity to positive infinity. Okay. And the range, what is that going to be? It's going to be from 0 to positive infinity. So here you see, domain is all value of x. So it just go from the left to the right, right? You see that it doesn't have any hole, any break point or something like that. It just go from left to the right and smoothly. For the range, it just going from like from 0, but not touch 0, and it keep going up, right? See that? So that's why it says the range is from 0 to positive infinity. Okay, so another case I want to write, remember that the left hand side I did draw is okay, that's b greater than 1. But for the second one, I want to write, I want to draw for the case that's b greater than 0 and less than 1. Okay. I should also mention that b greater than 0 and also b not equal to 1, right? Okay. So so for the case that b greater than 0 but less than 1, the graph had to be going from the left is from like positive infinity and going down, oops, too quick, going down, and let's keep going like that along with the x-axis. And the intersection here is a y-intercept going to be 0, p0s are the same with the left-hand side graph. And And what else? And asymptote still here. But this is going down, and we call exponential decay. Decay. Domain, in this case, what is that going to be? Still, it's still from the left to the right smoothly. So we're just going to say still a real number, and it's from negative infinity to positive infinity. And the range, okay, so look like it's from very high over here and going down, right? You see that? But it will never touch zero. So again, the range is just from 0 to positive infinity. Okay. For the interval, we always write the small number first, and then the higher values after that. Okay, so that's a line. We start with 0 here and then positive infinity. Okay, that's it is. Let's move down. Oops. Okay. Consider a population of bacteria that double every hours. If the number of bacteria at time t is ft, where t is measured in hours and the initial population is f of 0 equal to 1000, find a function that describes the population of bacteria at any time t. Okay, so you should remember that this this should, let me see, let me make sure. Consider a population double every hour. Okay, okay, and whole population here. So since it's a double every hour, then we should say like, okay, for the f of 0 over here, we should have f of 0 equal to 1000, right? What about f of 1? We're gonna double it, right? Let's say 2 times 1000. Then I have 2 times f of 0, right? What else? I have, what about another number 2? I mean, f of 2. I'm gonna have 2 times with ever 1, right? Maybe I rewrite like this better. Okay, let me, for the f of 1, I'm gonna write as 2 times f of 0, right? It's gonna be 2 times 1000. And then the f of 2 gonna be 2 times f of 1, which equal to 2 times 2 times 2f0. See that? Or maybe I can rewrite over here as 2 times 1000, right? And I can rewrite it as 2 squared times f0, right? Because when I combine to this, and f0 was 1000, right? So what about f of 3? I will have 2 times f of 2, and now it's become 2 times 2 square f of 0 over here, right? And then it's going to be 2 to the power third times f0, right? And if we keep going like that until say f of t, right? Then what happens? You want to say 2, you're going to have that, and you're going to multiply it by, I mean, 2 here should be 2 power t, right? Because you see like for f3, then 2 to power 3, right? So I have 2 to power 2 to power t times f of 0, which is 1000. 1000, right? Okay, or I can rewrite in a nice way as 1000 times 2t as a form of exponential function p0 times bt mt with that. Okay, so that should be the function that describes the population of bacteria at any time t, right? Okay. So let's move down to example number 2. A bacteria culture starts with 500 bacteria and doubles in size every half hour. So how many bacteria are there after 3 hours? So we have F0 equal to 500. Okay, right? You start with, because it said that bacteria start with 500. Okay. And it's gonna be doubles inside every half hour. Okay. So I'm gonna have let's say in every half hour. So you're gonna subtract a half hour. No, you're gonna add in 1/2 hour. So you're gonna have 1/2 and then 2 times 500, which is equal to 1000. Or I'm gonna rewrite as 2 times F0. Okay. What else? If I have adding 1/2 hour, 1/2 hour, I have F of 1. Then I have to multiply double the F, double the F of 1/2. Which, oops, which gonna give me 2 times 2 of F0. Okay. Or I can just substitute as 2 times 1000, which equal to 2000. Right. Because this actually looking for the how many bacteria, so I don't even need this one. I don't even need this guy. I can just right away have the number. Okay. Okay. So I have the after 3 hours. So I need to find after 3 hours. Okay, so I need to maybe I need to make it smaller. So I make 2 times 1000 here going to be equal to 2000. And this is going to be gone. What else? F, now F of 1/2. F of 1/2, right? Okay, let me have F of 1/2, or I say 1.5. 1.5. Then that's going to be equal to 2 times 2000, will equal to 4000. F of 2, if I add a half more, right? Going to be 2 times 4000, 8000. Right? F of 2/2, and that's going to be 2 times 8000, going to be 16,000. And lastly, F of 3 going to be 2 times 16,000, going to be 32,000. And that should be the answer for the first question. All right, so how many bacteria are there after 3 hours? Okay, so according to previous problem, sorry, you can see that every hour there are two doubling periods. Right. So that means what? That means at time t, at time t, right? At time t, there are 2t doubling period. Okay. So so what we have? We're gonna have f of t time with 500 equal to 500 multiplied by 2 to power 2t. So as you see, every hour, right? So let's say here's initial one, and then 1 hour after that, you have 2000 because you actually like multiply 2 times 500. Okay, so yeah. Okay, so in here we can see that P 0 equal to 500, and base in here P equal to 2. Okay, and we have the periods is 2t is doubling the period per hour. So because of doubling, period per hour. Okay. So per hours, we're doubling period. Okay. Okay. So now question is, how many bacteria are there after 40 minutes? In order to do this, we need to convert this 40 minutes to be the hours. So you know that 40 minutes multiplied by 1/60, which equal to 3 hours. Okay. So so now you can apply f up to third will be equal to 500 times 2 to power 2 times 2/3. Okay, so now you will have use a calculator and try to do operation correctly. So let me show you if I use calculator. So TI-83, I'm gonna use TI-83 here. Okay, so this is gonna be the way you do with TI-83. You have 500 multiplied by, make sure I have parentheses, 2 close parentheses to power, another parentheses, 2 times 2 divided by 3 close parentheses. Then you have, it's supposed to be 1259.9 something. So I'm gonna just like estimate it to be 1260 bacteria, because it's like supposed to be a whole number. Okay, so let's go down to the next problem. Okay, so example 3. Suppose we start with 100 bacteria. The size of the bacteria population was recorded at hourly interval. The number of bacteria n is a function of time t, so that n equal to ft. All right. So this is a table, right? And suppose the biologist change her point of view and become interested in time required for the population to reach various level. In other words, she is thinking of t as a function of n. So, so then, what does that mean? It's gonna be the inverse. Let me see. Inverse function of the function above, right? So it's gonna be what? Equal to f inverse of n, right? So function of g's, I'm gonna write as I'm gonna say function of g's is the inverse function. Function g is inverse of f of write this of f, and we can write it as f to power -1, right? So we write f over 1, who is f inverse. Okay, and t equal to f inverse of n, we actually mean n equal to f of t. Okay. So for 550 over here will actually gonna give me 550 will give me f of 6, right? F of 6. Okay. Now, for the first table, let's say from the first table to make sure people don't confuse it. But from the second table, I'm gonna have 6 equal to f inverse of 550 from second table. Okay. All right. Do that. Note. Not all functions have inverse. Okay. So down here is some figure that tell you how the function can be can have like can a function has an inverse or not, right? So for the left hand side over here, this f have seen have like for one input you're gonna get one output, something like that, right? One input, you're gonna have exactly one output. So that's the reason why you can have an inverse. So in here it says f has an inverse. Okay. What about the second one? We have 5 return to 1, right? If you want to have 5, you return to, it could be return to 1, or it could be return to -1. So from 2 number of the domain is have 1 range, so you cannot go back, right? And that make g, let's call this function is g, does not have an inverse. Because where does 5 return to, right? Okay. So if you see that a domain go to two number of domain go to one number up from the range, then that means you don't have the inverse. Okay. Now, question is how to find the inverse function of a 1-to-1 function f. We have followed 3 steps here. First, write y equal to f of x, right? Second, solve this equation for x in terms of y, if possible. Okay, and third step, to express f negative 1 or f inverse as a function of x, interchange x and y. The result equation is y equal to f inverse of x. So let's follow these 3 steps and we gonna solve the example number 4. So step 1, okay, step 1, I want to write y equal to x over 5 minus 4, right? Step 2, I'm going to solve this equation for x. So solve for x. What does that mean? I'm gonna separate x or isolate x alone. So I'm gonna add both sides by 4. So I have y plus 4 equal to x fifth. And then I'm gonna I have to lower down the power by fifth root both hand side. Fifth root both hand side. Right. Okay. Remember that scene. We are taking the odd index root, so we don't have to worry about the absolute value. Okay. So now I can. Now I'm having I am having a solution of x already, solution of x in terms of y already, right? Now we come to step number 3, and I'm gonna express f inverse gonna be as a function of x by interchange x and y. So interchange gonna be x cube root of x plus 4 equal to y, right? And equal to f inverse of x, which one more time I'm gonna write as f inverse of x will be equal to fifth root of x plus 4. And I'm gonna circle this because it is an answer. Okay. So let's move down. Okay. So if we look at the graph, note that fa equal to b if and only if f inverse of b equal to a, and thus the points a, the point ab, a comma b, where's a comma b? Oh, here, right? Is on the graph of f if and only if the point b comma a is on the graph f inverse. Okay. We get the point b comma a from a comma b by reflecting about the line y equal to x. Okay, so let's have so you can see that this is a perpendicular line, right? This one over here is a perpendicular line, and you can see that to this segment they are equal each other, right? And then a comma b and b comma a, they are inverse each other, right? Yep, they're just reflecting by the y equal x. So so then in here also the graph of f inverse is obtained by reflecting the graph of f about the line y equal x. So you can see so say here for here, if you want to find the inverse of that, you're gonna just have a perpendicular line go through this y equal to x, and then the reflecting point over here will be inversed. Okay, similarly, let's say here this point on the f, and if I want to find the inverse point on the f inverse, I have to draw the perpendicular line, go through y equal to x, and then make sure these two segments equal each other. So then this point is on the f inverse. Okay, let's move. Okay, so this is an exercise that you can try. So you can pause my video and try it. Now I can start to solve it for you guys. Do you remember that find the inverse function? Step 1, you have to write the y equal to 1/2 x minus 1, right? And then step 2, you have y plus 1 equal to 1/2 x. I want to solve for x in terms of y, right? So I multiply by 2 both hand side. I have 2y plus 1 equal to x. Right? So now I have to do distribution, or actually, you know what? I gotta just keep like that. Say okay. So that is step 1, step 2 over here, and then step 3 is interchange x and y. I have 2x plus 2x plus 1 will be equal to y, which is the inverse function of x. Or I can rewrite as the inverse function going to be equal to 2 times x plus 1. Okay. This is good answer. All right. I hope you guys have the same answer. So for this exercise number 2, I would like to let you guys do it. But if you don't know how to do it, please go to my office and let me know. then we're gonna work on that. Okay. So I'm gonna move to logarithmic function. Actually, I'm gonna stop this section now, and we'll see you in the next tab. Okay.